All right, so in this video, we're going to talk about translation look-aside buffer, TLB. But before really getting into the detail of translation look-aside buffer, we need to first understand why do we need such a new hardware accelerated mechanism, a new technique, translation look-aside buffer. So recall that in our last lecture, in our last video, we've talked about the basics about paging mechanism, the basics about a memory page table. And it has some inherent, so while it has its own benefits, for example, improved flexibility, fine granularity, and also improved scalability, but at the same time, it also has its downsides. And the very first fundamental issue for the memory page table is the page table accesses are too slow. So let's next take a look at why the page tables are too slow. Okay, so here in this slide, it shows a protocol, which is the address translation steps. So let's zoom in from the hardware perspective. So from the hardware aspect, how to perform, how to support the memory access, or how to support the memory reference. As you can see, this protocol has 6 different steps. So in order to perform a specific memory access or memory reference, the very first step is you need to extract the VPN, which is a short of virtual page number, from the virtual address provided by the CPU, right? So this is a very first fundamental step. In order to perform this virtual address to physical address translation, you need the input. And this step number 1 is to provide the input, okay? And the next step, step number 2, is you wanna calculate the address of the page table entry based on the input, the feed of the virtual page number. Because if you wanna recall that in our last video recording, the major goal of a page table is to facilitate the virtual address to physical address translation. In order to perform a physical address access, you need to translate the information. You need to translate the virtual address. And in order to translate the virtual address, you need the corresponding page table information. And the second step is based on the virtual page number, which is essentially the index, okay, of page table. You use this information to calculate the page table entry, okay? So this is step number 2. And step number 3 is to fetch the content from this specific page table entry. The core content of the page table entry is what? Recall in our last video, we've talked about the core content is the physical frame number. So as the next step, which is step number 4, is to just extract this core content from this specific page table entry indexed by the physical frame number. Okay, so this essentially is the physical frame number. So this is step number 4. As the next step is what? So we've already collected all the necessary information that we need to construct the physical address. So the next step, step number 5, is to just construct such a physical address. And then as the last step, which is step number 6, is to fetch the data under this specific physical address just constructed, right? To fetch the content into the memory, into the CPU register. Okay, so that completes this a memory access protocol, 6-step memory access protocol. So the next question you may want to ask is, which steps out of these 6 different steps are expensive, right? Which steps are expensive? Which steps are cheap? Well, as you can see in this slide, step number 3, as well as step number 6, these 2 steps are expensive. Why is that? This is because step number 3 and step number 6, both of these two different steps, they are essentially doing the physical memory access. So accessing something stored within the physical memory is obviously extremely significantly slower compared to, let's say, extracting, generating the virtual address from the CPU or accessing some on-CPU hardware, right? So accessing the memory is dramatically slower compared to that. So these steps, they are essentially memory accesses, okay? So that is why these two steps are extremely expensive. So the next question that you might want to ask is, out of these two expensive steps, which steps can we eliminate, could be eliminated, right? So we have step number 3 to, fetch the content in order to perform the virtual address to physical address translation. So this is corresponding with some page table operation. And the second, step number 6, which is to fetch the ultimate, the target, the destination data that you want to fetch from the physical memory and load it into the memory. So which steps can we avoid? Well, the second step, the second expensive step, which is step number 6. This is essentially the ultimate purpose of this physical memory access, which cannot be effectively eliminated, cannot be avoidable, right? Because this is a whole purpose, which cannot be avoided. So the first expensive step, which is step number 3, fetch the page table entry could be avoided, could be eliminated, because this is just for fetching the page table entry that is essentially stored within the memory. So this is just, in other words, this is just to facilitate the virtual address to the physical address translation. This is one of the steps for supporting that. So this could be hopefully effectively eliminated. But the question is how, right? So before answering the how question, so let's take a look at another example, which is an array iterator. In this example, you're provided with a simple C-based code snippet, which is called array.c. Okay, so this array.c, the core logic has exactly 4 lines of code. So the first line is to just declare a local variable, which is called sum. And then the control flow directly enter this for loop. This for loop has exactly n iterations. So within each iteration, it does nothing but try to aggregate the values from each element within this array, which is called A, right? This A array. Aggregate the values of each element of this array and calculate the sum of it and assign the value to the local variable, which is called sum. Okay, so this is what it does. Array iterator. And to compile it, just use this command line, okay, using GCC. And then in order to zoom in and examine the exact, assembly code instructions, you can use obj dump, object dump, if you are running the code within the Linux box, or if you're using MacBook, you can use a tool called O2, okay, whichever are best suited. So in this slide, it shows if you want to trace the virtual memory access, this shows the memory access patterns. It shows the virtual memory access patterns, okay? So as this is nothing but an array iterator, it tries to aggregate the values within the array. So this is essentially the memory read operations or memory load, okay? Memory load. So this is just virtual address. But essentially under the hood within operating system, the operating system is responsible for really getting into that, getting access into the physical memory. So to translate the virtual address to the physical address, on the right-hand side, this new column shows the corresponding physical access patterns, right? So the very first observation that you may make is each virtual axis gets effectively translated into two physical axes. Why is that, right? Because the very first memory axis is for what? Because you need to translate the hardware doesn't understand virtual address. You need to perform this virtual address to physical address translation. So you need the page table, which is any memory data structure that is residing within the memory. Okay, so you need to fetch the page table entry, which is one element within the page table. Okay, so this is a very first physical memory access. Okay, so since we're essentially touching the same virtual page, which starts with the high bits, which is essentially 3. The high bits information is 3. So this implies we're essentially touching only one single virtual page. So that is why the low bits, they are essentially the same, which has an offset of C, because we're looking into one single individual page table entry. Okay, and then the next step is to construct the physical address. And the very first sub-step to construct the physical address is to translate the virtual page number into the physical frame number in this case. So the virtual page number is 3, right? And this effectively translated into the physical frame number, which is the high bits information of the second physical memory access associated with each and every virtual memory access, which is 7. Okay. So this is a translated physical frame number. But before the second physical access ever happens. And then you need to construct the physical address, and then you can perform the physical access, physical memory reference. And then there we go. This is the second memory access. You try to access the corresponding array element, AI, under index I. Okay, so how to access that particular element has something to do with this offset. These are called frame offset, which is essentially the same as page offset. As you perform the translation, this page offset is only information that stays constant. Doesn't have to be changed. Okay, so what are the takeaways of this example? So there are 2 basic takeaways. So the very first takeaway, as I've already mentioned, is for each and every virtual memory access, it essentially gets translated into 2 physical memory accesses, okay, which is costly and which is the source of that slowness that incurred if you want to use a page table to facilitate this kind of virtual memory to physical memory translation. And this is the first takeaway. And the second takeaway is, as you can see, the second important takeaway, also the second insight, is there are some repetitive memory access patterns, right? So the very first physical memory access, which is trying to access the corresponding page table entry to fetch the virtual page number to physical frame number translation information, these steps are essentially repeated, which implies that for this repetitive memory access patterns, it could be cached by some special purpose hardware accelerator, hardware cache, which is what? Which is translation local site buffer, right?